We want to now look at actually performing the entire hypothesis test from start to finish using the critical value method. So whenever we look at this, we first want to state the null and alternative hypotheses. Well, the null hypothesis is going to be the easiest one. It's always mu equals some value. Our alternative hypothesis, that's where we have to determine, is it a left-tailed, right-tailed, or not equal to? We have to be careful here. Now remember, whatever number I put here, that's going to be the exact same number that goes here. And so whenever we do that, we call this mu sub 0. It's our starting point. Again, it's the value that we believe to be true. When we start to actually do our calculations, we need to find our significance level, alpha equals, and we need to find our critical value, which most of the time I just say critical value is equal to, and we again have to be careful if it is a left-tailed, right-tailed, or two-tailed. We shade in the diagram whichever side it is. Then we compute the test statistic. For this particular case, we're looking at z's. That's going to be our sample mean minus the mean that we put here in the hypotheses divided by our standard deviation over the square root of n. And I'm going to go ahead and put in those extra sets of parentheses to remind us to be careful with that calculation. Based on our test statistic, and if you want to, you can do ZT, that's our test statistic, we determine whether to reject or not reject. Now, if the Z sub T is in the shaded region, then we reject the null hypothesis. If Z sub T is not in shaded region, then do not reject the null hypothesis. Our last step is to state our conclusion. It makes more sense where we have an actual example in front of us. Our conclusion is basically what happens to the information that we're given in the original problem. Do we support it? Do we not? Do we say that it's different from? Things of that nature. So let's look at an example and walk through the entire process from beginning to end. Okay, so CNN Money reports that the mean cost of a speeding ticket, including court fees, was $150 in 2002. A local police department claims that this amount has increased. To test their claim, they collect data from a simple random sample of 160 drivers who have been fined for speeding in the last year, and find that they paid a mean of $154 per ticket. Assuming that the population standard deviation is $17.54, is there sufficient evidence to support the police department's claim at the 0.01 level of significance? Now, let's go back and look at some key points here. Population standard deviation. So we know the population standard deviation, so we're going to be using a Z test. That is our sigma, 1754. The 0.01 level of significance, that is your alpha, 0.01. Simple random sample of 160, that is your N. Mean price of $154 per ticket. Now this was from the sample of 160, so that is our X bar, our sample mean, $154. Now, they reported that the mean cost in 2002 was 150. That is our mu. That is our population mean. So these are the 5 pieces of information that we need to know when we're looking at hypothesis testing. The other piece of information that we need to know is local police department claims that this amount has increased. If it has increased, does that mean that it's going to be a less than or greater than? Well, an increase signifies a greater than. So we're going to put mu here. We're going to put an equal to, and then we're going to look over here. This is our mu. This is what we start with, $150. That's our starting point. So since this is a greater than, I'm going to actually go ahead and skip down here to sketch the diagram to help us out a little bit. Greater than signifies that it's a right-tailed test. Okay? So our alpha is 0.01. Since this is a Z, sigma is known, when I come over to my chart, I can look at this table 9.1. I'm looking at the right-tailed test over here. So I'm looking at this one. And our level of significance was 0.01. So my critical value is going to be a positive 2.326. So I'm going to go back. Critical value is a positive 2.326. And I'm going to put that down here. I'm putting my critical value underneath here. Okay? Now let's look at our test statistic. Our test statistic, Z sub t, is x bar minus the mean divided by our sigma square root of n. So we have that they calculated to be $154 minus what it originally was of $150. The population standard deviation is 17.54, and we had a sample of 160. Now again, I'm going to put parentheses around here just to remind me whenever I'm doing the calculations. I want to find that numerator first, 154 minus 150, that's going to be 4. I want to find 17.54 divided by the square root of 160, which is approximately 1.38666. Then I'm going to do this division. When I do this, I get 2.88. And I'm going to change my colors here because whenever I want to look at this, 2.88. Well, if here's 0, 2.88 is going to be down here. Is this in my critical region? Is this in the shaded area? Yes. So you reject the null hypothesis. When we begin to talk about the conclusion, what were we even discussing? We said that a local police department claims that the amount has increased. So we were claiming this. We rejected the null hypothesis, so I'm going to kind of mark it out. We rejected it, we got rid of it. Is the price of the speeding tickets greater than 150 now? Yes, because we are keeping this one. So, since we rejected the null hypothesis, there is sufficient evidence at the 0.01 level of significance that the mean cost of speeding tickets. That might help if I could spell correctly there. Let's try that again. Speeding tickets has increased. Because we rejected it, there is sufficient evidence to say that it has increased. Now, let's look at the possibility if we had said there was not, that we did not reject it. The only difference is we would change it to there is not sufficient evidence to state that it had increased. That's our only difference with our conclusions is we reject, there is. Do not reject, there is not. So I want you to try one or two of these, and then whenever we come back, we're going to look at a second method of calculating our hypothesis testing.